about varieties over finite fields. So let me remind you first the theorem that I talked about 2 days ago. So let me just write down the statement again. So this was the Bertini theorem over the finite field. So X was a smooth quasi-projective subscheme. And this is all over a finite field, so FQ. And I want to estimate the probability that if I take a hypersurface at random, what is the probability that it cuts X in something smooth? So I let script P be the set of homogeneous polynomials in the homogeneous coordinate ring such that the hypersurface defined by F intersects X in something smooth, so smooth of dimension n-1. And then I had a notion of density, which was defined by looking at the finitely many polynomials of degree d and asking what fraction of those have the property, and then taking the limit as d goes to infinity. And the theorem was that this was given by a value of the zeta function, the inverse of that. And so in particular, it's positive, so it proves that such f exists over the ground field. Okay, so the first thing I want to say is that the method used to prove this can be used to prove some slight generalizations of this. For example, you can require that the hypersurface h sub f, pass through a prescribed finite set of points. So if S is finite, so is a finite set of closed points. Then we can require to the hypersurface to pass through all the points in S. I mean, that's going to change. So if you remember the proof will work exactly the same way, except that the conditions at these points will be slightly different. So in the infinite product, you'll have some terms that have changed. So in fact, you'll get a different number here, but the proof will, other than that, the proof will work the same way. And in fact, you can specify more than just that it passed through these points. You can also specify the tangent directions of the tangent planes of the hypersurface at each of these points if you want to, as long as you don't do something stupid like require the tangent point on a point of X to contain the tangent space of X. Because if you do that, then there's no way you're going to get a smooth intersection. But as long as you don't impose something contradictory, then you'll still have a positive density. Okay, so now what I want to, so maybe I should also say something. Several people asked me, since the last time I gave the proof only in the case of P2 embedded into P2, or A2 embedded into P2. A lot of people ask me how much harder is the proof in the general case, and the answer is it's pretty much the same. So it's not that much harder. The steps are pretty much the same. I mean, you have to do a little more algebraic geometry, but if you know what you're doing, then it's pretty much the same. Okay, so all right. So now let me discuss some applications of these theorems. Well, actually, the applications will mostly use these strengthened versions, where you can specify something about give some additional restrictions on the hypersurface. So the first application will be sort of well, okay, the first application will be what I'll call an anti-Bertini theorem. First, actually, before I give this, let me just for convenience, let me use the word nice. I'll call a variety nice if it's smooth, projective, and geometrically integral. I just don't have to write this all the time. Okay, so the first application, as I said, is an anti-Bertini theorem. So it might seem a little strange that I'm using a Bertini theorem to prove an anti-Bertini theorem, but this is what happens. Okay, so here's the problem. So given a positive integer, well, at least 2, and a finite field, so given a value of q, I want to find a counterexample to the Bertini theorem. I mean, I'm not going to find a counterexample to the theorem I actually proved, but I will find a counterexample to the version where you only allow where you ask a hyperplane and not a hypersurface, because that I said would I mentioned this last time that would not you could not expect to find H a hyperplane defined over the finite field, because. Okay, so in other words, so the counterexample will be given by a hypersurface, x. So a nice hypersurface. Well, it's nice in this sense, but it has the following nasty property, such that for every hyperplane, so H over the finite field in the projective space, such that for every hyperplane, the intersection of that hyperplane with x is not smooth, which is the same thing as saying that H is actually, every hyperplane is tangent to x. Okay, so how do you prove this? So I'll use the generalized Bertini theorem to find an f, to find a homogeneous polynomial, such that well, first of all, such that the hypersurface it defines, which f equals 0, is smooth, and also I'm going to use the generalized version in order to impose some extra conditions, namely such that it also has the same tangent space at certain points pi. I should have chosen these first. Actually, let me. Okay, actually I should have done several things first. So first, yeah, okay. So let me start over. So let me list all the hyperplanes. There are only finitely many. So let me list the hyperplanes. So H1 through say HT. And for each one, I'll pick a closed point on it. So I'll pick a closed point, P sub I on H sub I, and without loss of generality, I can assume that these are distinct, because each hyperplane has infinitely many closed points, so it's easy to choose distinct ones. So assume that the PI are distinct. So these are distinct. Okay, so now I choose, so I have all these hyperplanes. I've chosen a point on each one. And now I use the Bertini theorem to find a hypersurface that's, well, it's not a very good picture, but okay. Actually, it's a really bad picture, but it's supposed to be tangent to these points. Okay, so anyway, so that's, and then I'll call that x. So let x be. So let x be this hypersurface. And so the Bertini theorem let me make it smooth, and it also has the same tangent space as h sub I. Yeah. How am I actually using it? I'm using it, I'm applying it to Pn inside Pn in order to guarantee that I can make this smooth, make f equals 0 smooth, and well, and then I'm using the generalized version to say not only is this smooth, but it also has the same tangent space. I mean, it's sort of like the example I gave last time, where if you apply it to P2 and P2, then the Bertini theorem gives you the density of smooth plane curves. So here I know there's a positive fraction of hypersurfaces in Pn that are smooth, and also there's still a positive fraction if I require it to have these particular tangent spaces at these points. Okay, so all right, so that's the proof. Yeah, it's a little funny in that the role of x and h is sort of, I mean, the Bertini theorem is used to construct x. So the x and the notation is sort of changed, but yeah, okay. So let me next give an application to what Nick Katz called space-filling curves. So the following application, this answers a question of Nick Katz. So now again given a nice variety. Okay, so given a nice variety of dimension at least, so let's say a dimension at least 1. The problem is, so then the theorem is that then there exists a nice curve y contained in x such that y passes through all the FQ points, all the points in x. Now, of course, I don't mean all the closed points of x, but I mean all the points, all the FQ points. So there are finally many points. So you could imagine applying this to, say, P3 or something, and then you find a curve that passes through all the FQ points in P3. Yes. Sorry, I couldn't hear. So why did I impose, okay, the condition n greater than or equal to 2? It was in order to, okay, I guess it was in order to guarantee that this x would actually be, so I guess, yeah, it was in order to guarantee that this x would be nice. In other words, in particular, that would be irreducible. If n were 1, then the hypersurface in P1 would actually be a finite set of points. And it might not be clear that you could choose it so that so the x would not be, so it would be difficult to guarantee that x would be irreducible. In fact, it would not be irreducible if the degree were greater than 1. It would not be geometrically, it would not be geometrically integral. But here it has to be irreducible because it has to be nice, because otherwise, if it had more than one component, then it wouldn't be smooth. Okay, did that answer your question? Yeah? Okay. So here, okay, so here I want dimension greater than or equal to 1, and the proof, okay, so the proof here, so maybe you can guess what I'm going to do. So I want to, I'll just keep cutting x with hypersurfaces. So the Bertini theorem will guarantee, so use Bertini to to cut x repeatedly, so with hypersurfaces. Passing through this finite set of points. You have to do a little bit of work to, I mean, you have to think a little bit. I'm not giving every detail. I mean, you have to do a little work to make sure that this curve you get at the end is also irreducible. But yes?
Is it known if there exists
A rational curve that passes through all the points. Well, I mean, it would depend on, I mean, it depends what x is. I mean, if x is, I mean, it might be that x has no rational curves on it, I guess. It could. So if, I mean, if x were something like a projective space, then, well, actually, I kind of doubt it because, I mean, if you want it to be a smooth rational curve, that's going to limit. Okay. Okay, so yeah, so the idea is you take x, you cut it with a hypersurface, so then you have a smaller dimensional variety, but because you chose the hypersurface to pass through all the FQ points, that new intersection still contains all the FQ points. So now you do it again. You take this intersection and you intersect it with a new hypersurface, still making sure that each hypersurface you use to cut down the dimension passes through these points. So eventually you get down to a one-dimensional case. You get it down to a curve passing through all the points. Okay, so that's it. So actually, so today's lecture is going to be a lot easier than Tuesday. There's not going to be any big proof. So you can also do sort of the opposite. You can find varieties that avoid rational points. So given a nice variety x over fq of dimension m, and given a positive integer, so an integer y in the range from 1 to m minus 1 inclusive, there exists a nice variety y in x of dimension little y, and such that it misses all the rational points. So it misses such that y of fq is empty. And the proof is, again, well, essentially, okay, it's just essentially the same. I mean, you repeatedly cut x with hypersurfaces. But this time, the conditions you pose, you force the hypersurface not to pass through any of the finitely many points on fq points of x. And in fact, you only have to impose that at the first stage, because then once you miss all of them, then there's nothing left to miss. So you just keep cutting by hypersurfaces until you get down to the dimension that you wanted. Okay, so maybe one more application before I move on. So this is abelian varieties as quotients of Jacobians. Now I should say it's already known that every Jacobian, I mean even over a finite field, that every abelian variety can be represented as a quotient of a Jacobian, of some curve. But what I want to say here is something slightly stronger, namely that given an abelian variety, so A over F2 of positive dimension, there exists a nice curve contained in A. So that's the difference. That I'm going to insist that the curve I use be actually inside A. And then such that the induced map from the Jacobian of that curve to A is surjective. And so hence A will be a quotient of that Jacobian. So the proof uses a trick that I learned from Offer-Gaber. So the trick is this: you pick a prime L not equal to the characteristic of your ground field, and then so I'm going to use the same idea as in the proof of the space filling curves, except what I'm going to do is arrange that this curve passes through. I'm going to cut it down with hypersurfaces to get a curve to get x that passes through, to get x passing through all the L torsion points. So A of in the L torsion points over the algebraic closure. Okay, so you can certainly do this in the same way I did it here. You get a nice curve. Now the only question is, why does that imply that this Jacobian is surjective? So okay, so the Jacobian. I mean, one way of thinking about this is if you view this Jacobian as the Albanese variety of A, then by the universal property of the Albanese, whenever you have any map from the X into an abelian variety, say mapping. Well, okay. I mean, if you want, you can assume that it maps a certain particular point to the origin. Then, I mean, you automatically get the map from XA will automatically factor through the Jacobian. I mean, another way of thinking, if you're thinking of this in terms of divisor classes and so on, then a point here is represented by a divisor of degree 0. You take each point, you map it to A, and you take the corresponding combination. Now that's another way of describing it. Okay, so why is this? So why does this work if you take all the L torsion points? So the idea is if you let B equal the image of this map, so then B is an abelian variety. It's an abelian subvariety. And it has the property that it has a lot of L torsion points. Has at least as many as L to the 2G, where G is the dimension of A, because B contains all the L torsion points of A. But I mean, you know how many L torsion points an abelian variety is supposed to have. I mean, since L is prime to the characteristic, it's supposed to have only L to the twice the dimension of B. So if it has this many, then the dimension of B, so this implies that the dimension of B must be at least G. And, well, it can't be any bigger than G. So, I mean, so that means that B is actually equal to A. Okay, so those are the applications I want to mention. So now let me move on to an analog of the Bertini theorem. Let's see. I want to mention the arithmetic analog that works for schemes of finite type over spec Z. So okay, everybody's seen this, right? Well, okay, maybe I should let that. Okay, so here's the arithmetic analog. So okay. So the arithmetic analog is actually not completely proven. In fact, it's pretty far from being proven. But I can at least say what the conjecture is. So if I have X, so now it's going to be a quasi-projective subscheme of Pn over spec Z. And now, so this is going to be the thing I'm going to be cutting with hypersurfaces. But and it turns out that the best analog of assuming it's smooth is to say that X is regular. So I'm going to assume that X. So X is a regular scheme of dimension. It's regular of dimension M at each closed point. So what this means is that that means that if you take the local ring, then this is a regular. It's a regular local ring of curl dimension M, and that means that this, first of all, this has dimension M, and if you take the maximal ideal modulo maximal ideal squared, so I'm sure most of you know this already. That if you take this, then this over the residue field, this is a vector space over the residue field, and that should equal the dimension of this ring, and it should equal M. Okay, so those are the assumptions, and okay, I was hoping this would be dry by the time I got. Okay, maybe I'll move on. Okay, and now I want to say what's the condition I want to have happen on the hypersurfaces that cut that? Oh, well, okay. So I wanted to define a set P as in the original Bertini theorem. Okay, so this is a continuation. I hope this is not too confusing. So I'm continuing the statement of the theorem, of the conjecture, sorry. So I'll let P be the set of homogeneous polynomials, F. But now, okay, so now they're going to be, so in the homogeneous ring of Pn over spec Z, so they're going to be polynomials in x0 through xn. And the condition is that the hyperplane it defines, in other words, proj of this ring modded out by the ideal generated by F, that this intersection should be regular. of dimension m minus 1 at each closed point. Okay, so that's the, and then there is some notion of density. Maybe I won't give all the details of the definition of density, but you can sort of imagine what it would be. In order to measure, how would you measure the density of a set like this? So you need to somehow fill this up as an increasing union of finite subsets in order to actually ask what fraction of elements in this ring satisfy the property. So one way would be to first restrict the degree, but also bound the coefficients and require the coefficients for that polynomial of that fixed degree to lie in some box, and then let the size of the box go to infinity, and also let the degree of the polynomial tend to infinity. And and then, well, there are various ways you can let those things go to infinity. So it's not, so there's several different notions that are maybe some more natural than others of density. But anyway, this is just a conjecture anyway, so I'm just not going to make it very precise. So with one of those notions of density, it should be true. In fact, no matter for any reasonable notion of density, it should be true that the same theorem holds, that this density should equal this. And you can do the same. So why do I expect this? I mean, the heuristic is essentially the same as before. You have this p is defined by a condition at every closed point of Pn over Z, and the probability that a given f satisfies the condition at a particular p is again given by that 1 minus 1 over the size of the residue field raised to the m plus 1. And so if you just believe that, again, that those conditions are independent, so and then you write down the infinite product of those probabilities, this is what you get. So, and then you have the hard part, and in fact, the beginning of the proof of this conjecture, well, which doesn't exist yet, but if it did exist, it would look pretty much like the proof of the Bertini theorem. You would start with the points of, well, now low degree would mean small residue field. So you look at the closed points of Pn over respect to Z that have small residue field, and you put a cutoff somewhere and look at the finally many closed points of low degree, and those you can handle in the usual way. You'll get using a Chinese remainder type theorem, and then you have the problem of showing that the error, that it's pretty rare for an intersection like this to be not regular at a point with a large residue field, and that's the part that I don't know how to do. I can almost do it if I assume the ABC conjecture, it turns out. But even with that, I wasn't quite able to do it. So you can get some partial results using the ABC conjecture. And the way, well, okay, I'm not sure if okay, maybe I can tell you a little bit of how the ABC conjecture comes in. Well, maybe I'll save it. Maybe I'll save it till the end if there's time. So I'll just leave this as a conjecture. But maybe I'll just do one example just to explain how this connects to. Well, no, I'll do two examples. Well, I'll just say one example is where X is actually a scheme of finite type over a finite field. I mean, such a thing is also, if you have a quasi-projective scheme over a finite field, you can also view it as a subscheme of Pn over respect to Z. And then this conjecture turns out to be just saying what we proved, the Bertini theorem up there. So, and another example is if you take n equals 0. So take a zero-dimensional projective space over Z, and you also let X be the same thing. Okay, so is contained in there. Now what is projective space? Zero-dimensional projective space? That's, well, if I were working over a field, that would just be a point. It would be just a speck of that field. If I'm working over Z, it's speck of Z. So this is actually speck of Z. Now what is? Okay, and I mean it satisfies the conditions. It's regular at each point because if you localize, if you take, okay, yeah, it's true. So and the dimension is 1, so m is equal to 1. And now what is a hypersurface in zero-dimensional projective space over spec z? It's going to be given by some equation, n equals 0, where n is an integer. So that's a hypersurface. So that's an integer. And now, what does it mean to say what does it mean to say that this is regular? So in other words, so h sub f is really spec of z mod nz. Okay, maybe I should call it h sub n. Okay, and this is regular if and only if. So if you just work out what the definition says, it turns out, it's regular of dimension 0 if and only if n is square free. So, because it's equivalent to asking for this to be reduced. So then the conjecture is just saying that the density of square free integers is what? Well, it's the zeta function of x evaluated at 1 plus 1. And you all know what 1 plus 1 is. And you probably know what the zeta function of spec z is also. That's the Riemann zeta function. So you get zeta of 2 inverse, so as expected. Okay, so at least the conjecture is true in that case. Okay. All right, so that's all I'll say about the conjecture for now. So now let me move on to other applications of the sieve method that have nothing to do with the Bertini theorem. So I'll go back to now varieties over finite fields, and I'll prove what I called the Whitney embedding theorem over a finite field. So the real Whitney embedding theorem is a theorem about differential manifolds, saying that if you have a smooth C infinity manifold, for example, I mean, you can weaken this a little bit. Of dimension m, you can embed it in Euclidean. You can embed it in Euclidean space of some dimension, 2m plus 1. Actually, Whitney proved that you could get it down to 2m. But algebraically, there's an algebraic analog of this. So this is there's just a classical theorem. I think it's too easy to have anybody's name attached to it. So let K be an infinite field, and let X be. Well, let me just talk about a curve first, just to make things even easier. So suppose I have a smooth quasi-projective curve. Over K. So then the theorem is that then there exists a closed immersion, so an embedding of X into P3. So for example, if you have any genus 1 curve over Q, for instance, you can always embed it in P3. The degree might be rather large, but it does embed. So the proof is a lot of you have seen this already. So it's quasi-projective, first of all. So you can start with some embedding. But it's probably not in P3. It's probably embedded in some huge projective space to begin with. And then, in order to get down to P3, the idea is to compose this embedding with sufficiently generic linear projections. Sorry? Oh, I shouldn't have said closed. Yeah, okay, so, yeah, okay. Okay, well, there, yeah. Yeah, if it's not closed, there's no way it's going to, if it's not projected, there's no way it's going to be a closed immersion, but, yeah, okay. Yeah, I have two choices. I could either erase this, or I could erase the quasi. Yeah. Okay, so let me, I'll compose with sufficiently generic linear projections. So from Pn to Pn minus 1, and so, okay, in order, more precisely, I'd project. So to give a projection from Pn to Pn minus 1, that's given by choosing a point in P sub n and projecting away from that point. So project from a point. And in order to make sure, so what I want to make sure is that when I compose this with this, that I still have an embedding. So, in order to do that, I have to make sure that the point is not such that when I project from that point, two of the points on X collapse, get pushed onto the same point of Pn minus 1, which means that the point I project from so the point in Pn should not lie on any secant of X. It should not lie on the line connecting any 2 points of X. So, and it should also not lie on a tangent to any point of X. Because I mean, I'm using the criterion for about separating points in tangent to get an immersion. I want to make sure it separates points and separates tangent vectors. So, all right. So I need to choose a point that lies off of the secant variety. So the secant variety, by definition, is the Zariski closure of the union of all the secants. And by taking the Zariski closure, you automatically get the tangents for free as limits of secants. So, and this is going to be possible as long as the secant variety is not all of Pn. And luckily, this, for a curve, the dimension of this is at most 3, because it's a union. I mean, it's given by a 2-dimensional family of lines. It's a union of it. So if n is at least 3, if n is greater than 3, then you're guaranteed to be able to find a point, and so you can lower the dimension. So as long as n is greater than 3, you can lower the dimension. So you can eventually get down to n equals 3. Now, where did I use the fact that k was infinite? That was to know that this small dimensional variety in P4 or higher did not go through all the k points, and that'll be true as long as k is infinite. But as you can guess, this might fail if you're a finite field, because as I've seen, you can have varieties that, even though they're of smaller dimension than the whole projective space, they can go through all the FQ points. And in fact, there's even easier reasons why this theorem fails for finite fields. Can anybody guess why this theorem can fail? The which? Oh yeah, the space-filling curves. Right. For example, if you're working over a finite field and you had a curve in P4 that went through all the FQ points of P4, there's no way you're going to embed that curve into P3, because your curve has more points, more FQ points than P3 does. So that's a problem. So that's one obstruction to this theorem. And there are other ones as well. So let me Can anybody think of another obstruction? So I'm saying, in other words, okay, suppose I choose a curve x, and suppose it has the number of FQ points it has is less than or equal to the number of points, FQ points of P3. So that's definitely necessary if you're going to embed x in P3. But there's some other necessary conditions. Okay, so we're saying that this theorem can fail if k is FQ for several reasons. One, as you were saying, it may happen that the number of points is greater than the number of points on P3. So there's something else that can happen. Anybody have an idea? There could be too many sequences. What? Yeah. Yeah, you could look at, right. Yeah, I mean, that is another thing that could happen. Yeah, I guess what I was thinking of, yeah, there could be more, what do you say? Yeah, there could be more FQ squared points. Even if the number of FQ points is okay, there might be too many FQ squared points. In fact, you can refine that even more by asking for the points that are whose residue field is exactly FQ squared. So you could actually count the, so it may happen that for some degree E, the number of closed points of degree E I mean, you can think of these as being Galois, if you want, you can think of these as being Galois conjugacy classes of points over FQ bar whose residue, but where the field of definition is FQ to the E, if you want to think of it that way. So it could happen that that number is greater than the corresponding number for P3. Okay, so whatever theorem is going to generalize this one for finite field is going to have to take these into account. And now the theorem is, there is a theorem that can be proved. So there's a theorem of my former student, Ni Nguyen. So, okay, I'll state the general version where you allow x to be not. Don't even assume it's a curve anymore. Just have any dimension, say m. So over a finite field fq. Then and choose an integer that's at least 2m plus 1. So that would be 3 if we're talking about a curve. And now let me suppose. Okay, then the conclusion is there exists an immersion from x into Pn if and only if there are no obstructions of this type. So as long as for all e greater than or equal to 1, the number of closed points of degree E on x is less than or equal to the corresponding number for Pn. So it's saying that if x embeds in Pn set theoretically, as far as the points in their residue fields are concerned, then the curve actually, or sorry, it's a variety now. The variety will embed in Pn. So how do you? So I'm not going to prove this in detail. I'm going to say, how do you prove this, and why does a sieve come in? So the idea is sort of similar to the proof in the infinite field case. You start with an embedding x in some big projective space. And now you want to choose a projection, a linear projection. Actually, let me now do the linear projection in one step. I'll go all the way from P capital N down to P little n. And the way I'll do it is I'll just choose a random projection. But it won't be a linear projection anymore, because there are only finitely many linear projections. And as you can imagine, if you have only finitely many projections, it could happen that all of them are bad. So I'll use sort of instead of using a linear map, I'll use a map of high degree, and I'll let the degree tend to infinity, in fact. So the idea is to show that if the degree is large, then if I look at the composition where I start with this embedding into a big projective space, and I compose with a random map to the little projective space given by some homogeneous polynomials of degree d. So in other words, for random f0 through f little n in the homogeneous coordinate ring of the big projective space, and of degree d. So I'll put a little subscript d to mean homogeneous of degree d. Then the problem, the conclusion is this is an immersion with positive probability. So okay, that's almost all I'm going to say about the proof. I mean, so how do you prove this? You want to do something like the Bertini theorem, but this is not a local condition anymore. If I choose these f's, you can't just check whether something's an immersion just by checking point by point. What you need to do is check pairs of points, just make sure that no 2 points on x get collapsed, get pushed to the same point here by this map. So you have now you do a sieve similar to the one I did on Tuesday, except you sieve over pairs of points. And you also have to check the condition about tangent, separating tangent vectors. And so that's another condition. So you do a big sieve, and you have, again, you cut up the region into where the 2 points are of small degree, where one of them maybe has small degree and the other one has big degree, or two of them have medium degree. Anyway, there are a lot of cases, and you eventually you prove this theorem. Okay, so yeah, so I shouldn't really call this a proof. So maybe this is like a proof idea. Okay, so the last thing I want to talk about is another construction involving finite, where the proof works for infinite fields, but again breaks down for finite fields, and we want to try to fix it. Yeah. Yes. To lower this one? No, I don't. Well, okay. I mean, the proof really uses this. I think it probably. Actually, I'm not really an expert on this, but I think probably even over an algebraic closed field, you can't really lower. You can't expect to lower this, because yeah, I mean, I guess, yeah, if you took. Yeah, it could be. I mean, but you could always try using a completely different projective embedding to start with. I mean, for example, here, yeah, if you start with x in p sub 2m plus 1, yeah, as you're saying, the secant variety, generically, it will be the whole thing. Because the secant variety, you expect to have dimension 2m plus 1. And if that's the case, then you won't be able to start with that embedding and project down to pn minus 1. You might hope that you could start all over. I mean, you throw away your initial embedding and use some other embedding and try to go down from there. But I think it's unlikely that would work. Yeah. Yeah. That's certainly true. That's a good point. Yeah. So even for curves, you can't. Most curves cannot be embedded in the plane, because as you say, there's a genus formula for. Oh, I see. You want to strengthen this condition and hope that will imply that you can put x in a smaller projective space. I kind of doubt it, but because of these problems with, yeah, it's just the geometry gets in the way. It's not the number of points anymore. It's just the overall geometry even over the algebraic closure that prevents you from doing. Okay, so let me see. All right, so let me see if I can state this last application of this method. So this is to the construction of Lefschetz pencils. So I'm going to explain what a Lefschetz pencil is, first of all. So I mean, the idea is if you're trying to study a smooth variety, one technique. Let's suppose this for okay. So then, one thing you can try to do is to choose f and g are homogeneous polynomials of the same degree. So you have degree some degree d, and choose them so that they define a dominant rational map. So a dominant rational map to P1. So in other words, the map is given by these two homogeneous polynomials. And then the idea is you could try to study, if you want to study x, you can do it by, you hope to do it by some sort of induction on the dimension. Because now you represent x as a one parameter family of n minus 1 dimensional variety. Well, not n, okay, of dimension 1 lower. And then if you can prove something for all the fibers of that map, then you hope maybe you can prove something about x. So, but there's some problems with this. Well, first of all, if you want to get first you should try to resolve this. This might be indeterminate at some point. So this is really just a rational map. Because f and g, there could be a locus where f and g are both 0 on x. And so really what I should do is I should blow up that locus. So blow up the indeterminacy locus. So that's where f and g, it's contained in this at least. So I'll blow up the locus where f and g are both 0. And when you do this, blowing up that subscheme, we get a family. So now I really have, from that blow up, I have really a morphism down to P1. And we get a family of hypersurface sections. So the fibers of that map to P1 are hypersurface sections of x. So let me call them x sub lambda. So they're parameterized by points on P1. And explicitly what this hypersurface section looks like is just, so this is just the intersection of x with the following hypersurface in Pn. Okay, now ideally, if you're trying to do some induction, you would want to have the fibers of this map have the same properties as x did. So in particular, if you're trying to prove something about smooth projective varieties, you would ideally want all the members of this family to be smooth. And while you can, by Bertini theorem, you can easily find one hypersurface section that's smooth, or even have most hypersurface sections in the family be smooth. But if you do the dimension counting, you'll find that generically you don't expect to be able to make every member of this family smooth. So a Lefschetz tensor is something that's the next best thing, and it's something that you can reasonably expect at least from the dimension counting, at least if you're working over an infinite field. So right. So yeah. So as I said, unfortunately, you might not. So here's a definition. So I'll call I'll say that this defines a Lefschetz pencil. If only the following conditions are satisfied. First of all, the axis, which is the place where f and g are 0, this should intersect x transversely. And second, at least it should be true that most of the members of this family are smooth. So all but finitely many x lambda are smooth. And you can ask for something even more, namely, you can try to control the singularities of the finitely many fibers that are bad. So, namely, each non-smooth x lambda has at most one singularity. Has only, well, okay, so these are the non-smooth ones. So they will have only one singularity. And that singularity is an ordinary double point. Yeah, probably I should really give this definition over k bar and then say that, okay, so anyway. So, and if k is infinite, so if k is infinite, then as I was saying, dimension counting shows that you can always find such things. Some of this, I mean, it's not a trivial argument, but it's some work. It shows that Lefschetz pencils exist. For every x. In fact, this is used in Deligne's proof of the Weil conjectures. I mean, even though he's proving something about finite fields, he had the freedom to enlarge the finite fields. So he only needed this statement over the algebraic over an algebraic closure of the finite field. So, anyway, yeah, so the theorem is, yeah, well, as you can guess, the theorem is, so this is also proved by my former student. Again, even if k is finite. Okay, so so time's up. So let me just mention, let me just try to summarize everything I did. So, or at least try to give some, I mean, I gave a lot of different examples of what these sieve methods could prove. And so what is the general principle that underlies all these? So, I mean, I don't really have a theorem about, I mean, I don't have one big, enormous theorem that contains all these examples of special cases, but I can sort of formulate a general principle that seems to apply in all these cases. And that's that whenever you can prove the existence of some polynomial or some sequence of polynomials over an infinite field, whenever you have an existence proof like this, that you can that involves dimension counting, where the proof is given by dimension counting, as in here or as in the proof of Bertini theorem, the classical Bertini theorem, if you know that proof. It seems that whenever the existence works in this way over an infinite field, using dimension counting, then you can prove an analog using this sieve method and using this closed point, the sieving by closed points. So I'd really like it if you could actually prove some big general theorem that would contain all these, but I don't know that yet. So anyway, I think there are probably a lot of other examples that I haven't really thought about, where there are theorems that say, at the beginning of the theorem it says, assume that K is an infinite field. And hopefully using this method, you can eliminate that condition. Okay, thank you for your attention.